Excellent. I think you notice there is a big difference now in terms of the quality of the recording when you compare this one to the previous setup. I think this is much, much better. Okay, so what we are supposed to cover this week. This week we will cover what we call basic concepts. What is current? What is voltage? What is AC? What is DC? What is power? What is energy? What are the different types of sources that you will be able or that you will be deal with? So all of these things will be covered. So by the end of this week, you will understand the basic idea of the terminologies that we'll be using during this term. So we'll start with an electric charge. An electric charge, this is, as we know from chemistry, that you have an atom, you have a nucleus, and you have electrons around them. Okay, so this is the most basic charge that we know, which is the charge of the electron, which is equal to 1.602 times 10 to minus 9 C. C stands for Coulomb. Coulomb is the charge unit that we will be using. Now, the charge cannot be neither created nor destroyed, but it is can be changed from one form into another. Now, we will not deal with the charge much in this course because the charge, it's very hard to measure, but instead there is another indication of the charge which we call it the current. What is the current? The current is the flow or the rate of flow or a change of the charges. So for example, when we have a conductor like this one, when we have charges that start to move inside this conductor, so we call this is the current, and to be more specific is the time rate of flow of electrical charge through a conductor or a circuit element. Now the current units are amperes. Okay, so ampere is the unit of the current. This is one of the most important units that you need to know, ampere. And this is, of course, named after one scientist. Now, what is 1 ampere equal to? It is 1 coulomb per second. So as you can see here, that the current is a flow of a charge, or we can describe it that I, the current, this is the symbol that we use in electrical engineering for the current, is equal to the rate of flow of the charge. So it's dq by dt. It's a derivative of the charge. So if the charges are standstill, they don't move, you have them but they don't move, then the dq by dt will equal to 0 and the current will be equal to 0. So for a current, to have a current in a circuit or in a wire, those charges they have to move. Now sometimes, not very often, but sometimes we need the charge instead of the current. So from this you can say that the dq is equal to I dt, and then can take the integration, so the q will become the integration of I dt. Now you can see here that the variables here in terms of dx, not in terms of dt, that's will not affect the results, but mathematicians, they don't like to have the limits symbol the same as the variables inside the integral. So usually we have it at different, but at the end of the day, the value of the charge will be a function of t, because of the t in the limit in the integration. It will be there in the formula as we will see. Now we have basically two main types of current. We have a direct current, meaning that the current value doesn't change with time. So look here, this is the y-axis is the current, the x-axis is the time. So you see here that the current at any moment, it's exactly the same. You measure the current now, after 10 seconds, 20 seconds, it doesn't change with time. And for the direct current, there are some sources and load. And these two important terminologies, a source and a load. A source is the place where you generate the current. The load is the place that is consuming this current. So we generate current to be consumed by the load. So a common sources for direct current is the batteries, either the ones that we use them in our remote controls, in our toys, etc. Those batteries, or the battery in the car. 12-volt battery gives you 12 volt. This is the volt. We'll talk about the volt later on, but this is also a direct current source, give you a current in that format. And for example, as a renewable energy source, the photovoltaic cells also convert the light into a direct current. Also, it provides us electricity in that format. For the loads, we have, let's say, this is the DC motor. Maybe if you have if you a hobby guy, you might have seen these type of motors in toys. You might have bought them to do certain things if this is of your interest. And there's some lamps also they work with DC. Now in this course, you can say that more than 50% we will be working on circuits that is supplied, energized by DC sources. Okay, and we will have certain type of analysis. I will talk about that, and we'll talk about that in details. So let me talk about this one again. So you have, we will have the source. This is my source. So these are examples of the source. Those will supply the current to the loads. The loads will consume this with, and the current will flow here and go through these loads and come back. We will have like a continuous circuit. Okay, so this is the direct current, and always this is something very important that you understand that the electricity, one of the drawbacks of the electricity that make it different than other commodities uh, like water, food, that when you produce it, you have to consume it. You cannot actually save it except very little quantities. Uh, I have some questions here. Let me answer them before I move forward. What consumes the current is the load. Why is the load required, and what happened if there is no load? If there is no load, means there will be like a voltage. I will show you an example in the next slide about what will happen if there is no load. Just bear with me. I will show you an example. But the other type of energy that we will be talking about is the AC. And that will be after the midterm. We will not talk about AC until after the midterm. And the AC, it is comes from alternating current. So as you can see here, the current is going up and down. So there is a positive cycle, positive cycle, negative cycle, and so on and so forth. Look here, here it's constant, doesn't change, and here it is going up and going down. Okay, now this is the main type of power that we use in our houses, in factories, in streets. This is the main source of energy. Okay, so the huge generators that we use to generate power, they generate power in this format. This is a small generators that you can take it to a camp or so, but also this type of generators, they're called diesel generators. Those are also supplying the AC, but the whole idea here uh, is that those, see, this is a person here, see how big is these generators. These are the main generators. It's either thermal power plants, or they are hydropower or nuclear power. So you have a huge amount of power that is produced. Now these are the loads. Now this is something familiar to us, which is the socket in the house. Now back to the question, what will happen if there is no load? Now, this is the top socket, nothing connected to it. So there is a voltage there, and we'll talk about voltage in a second, but there's no current flowing. Okay, so the power is ready to be consumed here. Now in the other socket, there is this plug-in which connect an appliances or an electronic device or anything else. So once you connect the power there, you are consuming it. So the power has been consumed in the other using the other socket. So if it's not consumed, it is standby here. It's waiting for you to connect your device to the socket, and then it will start the current start to flow from the circuit to supply your load. I think also have some couple of questions here. Now, does a negative current mean current going in the yes, exactly, it's current going into the opposite direction. So if we have here like the source, if we have here the source and we have here the load, so in DC the current goes here in one direction. In AC it goes in one cycle in this direction, in the other cycle it goes in the other direction, so it goes in both directions. So this is a basic difference between the AC and the DC, this DC power. Any other questions? Does the negative current mean current going in the opposite? Yes, this was what do we want AC instead? Why? Okay, that's a very, very good question. Why do want AC instead of DC? Okay, I will tell you a story at the end of today's lecture about AC versus DC. Why AC is more important than DC. Let's move on. So here it says that a conductor has a constant current of 5 amps. So we have 5 amps. So there is a conductor here. And in this conductor, there is 5 amps or 5 coulomb per second. So there are 5 coulomb pass through this conductor every second. It says how many electrons pass a fixed point. So if we have here a fixed point as reference, so we agreed now the current is nothing but the flow of electrons. So the electrons will be flowing through this fixed point. So we want to know in 1 minute how many electrons will cross this reference point. So we know that the current, the 5 amps, is equal to 5 coulomb per second. But first we want to have it in 1 minute. So in 1 minute we know that 60 seconds is equal to 1 minute. So we multiply by 60 seconds over 1 minute. So the second will cancel and this will have 300 coulomb per minute. So now we know that per minute how many charges in terms of coulombs pass in this conductor. Now I want to know how many electrons, but we know that 1 coulomb equal to 1.602 times 10 to minus 19. So this is 1 coulomb. So 300 coulomb is equal to how much? So that's what we want to find. Now 300 coulomb per minute. 300 coulomb per minute. If we divide it by 1.602 10 to minus coulomb per electron, now the coulomb will cancel with the coulomb and we'll have electron per minute. Now this is 1 electron, sorry, this is 1 electron. 1 electron is equal to this. Okay, so of this column, I think I wrote it the other way around. So 1 electron is equal to this column. So we want to know how many X electron will have 300 coulomb per minute. So this is what we want to find. So it is 1.87 times 10 to power 20 21. You have the answer there, so you don't need to worry about it. Now here, the other question says that we have the charge. The charge Q is equal to 4 times 10 to minus 3 sine 120 pi t, and this is in coulomb. So we want to find what is the current. If this is the charge, and this charge, as you can see clearly, it's a sinusoidal. It changes with time. So I want to find the current. We know that I is equal to dq by dt. So I need to take the derivative of this. Now, as you know, if you have a sine function, sine of, let's say, 2x, if you take the derivative of this, it is 2 times cosine 2x. So for this, it is, we keep the constant as it is, 4 times 10 to minus 3. Now this is times 120 pi times cosine 120 pi t. So this is your current, and the unit will be in amps. Again, as you see here, the answer is given to you. Now, in this example, it's the opposite now. Now we know the current. I of t is equal to either 0 or equal to e minus 2t milliamps when t is greater than t greater than 0 or equal to 0. So if it's less than 0, it's 0. So if we want to picture this, let's draw this first before we do the calculation. Let's try to picture this. So this is your x-axis, which is the time. So at less than 0, it is 0. It's here. Now at t equal to 0 is equal to this. If I substitute I equal to 0, this is equal to e to the minus of 2, 0, which is equal to 1. So this is equal to 1. Then after that, it is equal to e minus 2t, and this is an exponential decaying function, so you'll have the current equal to this. So here, the function here, it is e to the minus 2t. And as t increases more, you will have here a decreasing current. Now, what is this basically? We will see this later on. This is like we have a storage device. You are storing current, and then you are discharging. So the current was stored here at this point, and then you start to discharge this current. So that's just to give you an idea what this, and we will talk about this in details later on. Now we want to find the charge Q. Q, as we know it, is the integration. Now we want to find the charge from 0 to 1. So it's from 0 to 1 I dt or dx. It doesn't really matter. As I said, this is just for a variable. Now, since we have a limited integration, bounded integration, so I can have it dt. There's no problem. So this is equal to integration from 0 to 1 e minus 2t dt. Okay. So this is equal to minus, or let's do it slowly, 0 to 1 e minus 2t. So we can start the integration, minus 1/2 e minus 2t from 0 to 1. So this is the integration of e minus 2t. I'm hoping that you guys still remember the integration. So when you take the integration of e to the power of, let's say, ax, is equal to 1 over a e to the power of ax. Hopefully you remember these basic rules. Now, I'm expecting you to know these basic things, but we will not have these things into details. There will be like a question, but not here, not at this stage. Later on, when we talk about the capacitors and the inductors, which will be after the midterm, then we will come back to these things. But in in the first part of the course, I don't expect you, or I don't expect from you to ask you a question like this in the exams. So, but this is just to give you an idea. So the integration from 0 to 1, so this is equal to minus 1/2, then e minus 2 times 1 minus e minus 2 times 0. So this is what it is equal to. So this is equal to 1/2 minus 1/2 e to the power of minus 2 minus e to the power of 0, which is equal to 1. If we take this minus inside, so this is equal to 1/2 1 minus e minus minus 2. I think we have a lot of questions. Let's start to answer them one by one before we move to the next example. Okay. Okay. Could you please explain what happens when there is no load? When there is no load, there is no flow of current. So you have power standby, but there is no transaction. There is no flow of current. Like, for example, you ask your dad for money. Your dad has the money. Okay. So if you don't ask him, he will not transfer you. Transferring the money from your dad, wherever he lives, or your mom, or your brother, sister, whoever is sending you money, is the current. Now, the dad has the money, the mom has the money. They are standby, waiting for you. Same thing. The socket, they have the voltage or the power ready to be transferred. You didn't ask for it. You don't connect the socket, so it will be waiting there. And once you connect, there will be immediate transfer. So I hope that explains. Are we expected to solve these type of questions right away? I don't know answer what you mean by right away, but yes, you are expected to solve this question, but I will not, in the midterm, there will be no questions like this. We will come back to the integration and the derivative in some other applications. But this is good to understand. Where did you bound the, where did you bound of 1 come from? Why did we find I 0? Okay, now the question says here, we want to find the current, the charge that passes through, during the interval from 0 to 1. So the bounding from 0 to 1, this is in the question. So I want to know how much charge is flowing from 0 to 1. Now, why I did at 0, this is just to visualize the current. Here, I'd like just to visualize. So this is why I substitute with 0. And you will find that this is equal to 1 milliamp. When you substitute here with 0, so this is just to visualize the current. This is not required in the question, but this is only to visualize it. Now, what you found the integration from 0 to 1. So basically, you found the area under the curve. This is what you found. This is the amount of a charge in the current from 0 to 1. This is its amount. Okay, the interval. Okay. Okay, where did -1 come? Okay, this is the integration. This is the integration. The Q is equal to -1/2, like what I showed you here. When you do the integration of e to the power of a of x is 1 over a e to the power of ax. Okay, let me now ask you, this is the easiest bonus question you will ever have. What will be the unit? So please write down here, what is the unit? So the bonus is for the fastest one who get the right answer. And I have many answers. None of them is correct. All the answers so far are wrong. Yes. Come here. This is Emily Zoo. It's in millicoulomb. The answer is in millicoulomb. Why millicoulomb? Because the current is in milliamps, not in amps. If the current in amps, then yes, the charge will be in coulomb. Now, if I have the current in milliamps, then this has to be in millicoulomb. Okay, Emily, that's good. Congratulations for your bonus. Please, after the class, email me with your name and your ID. The most important thing is your ID, so that you will have your 0.5 bonus mark. Good job. Now, let's move on. Now, let's talk about something very important about the convention of the currents. This is something we need to understand very, very well. Now, although we know that the current is basically flow of electrons, and that's what is, maybe if you studied in you took a physics course, that's what they teach you, and this is the true current. The true current is the flow of electrons. However, it's now, for historical reasons, it is now universally accepted that the current is a flow of positive charges, and we will see the implications of this later on. But when we talk about there is actual current, which is a flow of electrons, which we will not use. But there is something called the conventional current, which is different than the actual current, which we assume that the current is basically the flow of the positive charges. Now, let's look here. When we say that I1 is equal to 2 amps in this direction, it means that the current is flowing in this direction, that is giving you in the arrow, and its value is 2 amps. However, if I give you that the current is equal to minus 3 amps and going in the same direction, this is equivalent, exactly the same, if I assume that the current is going in the reverse direction, but with a value is 3 amps. So these two are exactly the same. So a current going in one direction with a positive value, if you find it in, or assume it, or find it in the other direction, it will be a negative value, and vice versa. And this is extremely important, and we will see later on, once you start solving circuit, why this is very important for us. So here, these two currents are the same, because this current going in the reverse direction is this current, but it has minus 3 amps. So once I put it in the opposite direction, this would becomes 3 amps. So these two currents are exactly the same. For the currents to be the same, they have to match two things, direction and magnitude. So both, they have to be exactly the same thing. So a current, if I say in a circuit that I have a current going this direction equal to minus 3 amps, or I said that the current going in this direction with 3 amps, both answers are correct. I don't need to fix this. Just saying this, it is understood that the current will be 3 amps and it will be in the other direction. Now, that's all I want to say about the current. So current is the rate of flow of electrons. The current is equal to dq by dt. The current that we will use in this course called the conventional current, which is a flow of positive charges, not the actual current, which is the flow of electrons or negative charges. And the current direction is giving as an arrow, as a flow of something. And if I reverse the direction, then I have to change the sign of the current. So that's all you need to know about the current. Let's talk about the driving force of the current. What will make the current flow in a circuit? You need to spend energy to make these electrons flowing. We know that if I have this piece of plastic, or if this is a conductor, it doesn't really matter. As such, there is no flow of currents. There is nothing is flowing here. There are electrons, there are positive charges, but they are not moving. To make them move, I have to spend energy so that these electrons can start moving. And this is the voltage. The voltage is the energy required to move a unit charge through an element. and its magnitude is voltage. So the voltage between 2 points is the dW by dQ, or the derivative of the energy with respect to the charge. So let's understand this more. So when we spend 1 joule of work, or when a 1 joule of work is required to move 1 coulomb between point A and point B, then the voltage will have is 1 volt between A and B. So if we require to move 1 coulomb charges, because remember, charges is currents. So if I want to move this amount of a charge or this current, then, and I needed 1 joule, then there is a voltage equal to 1 volt between A and B. Now, when you look here, the voltage is between 2 points. The current is a flow of electrons. The voltage can be between two points in the circuit. So the voltage again can be positive or can be negative. Now, as we did in the current, we said that if the current is positive, if I reverse the direction, it becomes negative. The voltage is polarity. So here the voltage between A and B, but plus minus means that the polarity of A is higher than the polarity of B. So this is plus and minus. But here the V is equal to minus 5 volt. So basically this is equal to this. So what we did here, we changed the sign to 5 volt, but also at the same time we flipped the polarity. So basically B is actually higher than A. When you look to that, so actually A and B are the same thing. This and this, they are exactly the same potential or the same voltage. When you look to the C and D, plus and minus, this is 5 volt. So if I reverse the polarity, it becomes equal to minus 5 volt. So basically here is, we say that A is higher than B by 5 volt. And here I'm saying that B is less than A by 5 volt, or A is more than A by minus 5 volt. Same like I said, I have more money than you by $10, or you have more money than me by minus $10. So this is the same way of saying the same thing. So the polarity here, it is positive or negative. The current direction going from right to left or left to right, we need to reverse it once we change the voltage. Let's re-emphasize then here. So the positive and negative signs define the reference polarity. So here we say that A has higher voltage than B. Okay, this is higher than B. And if the number is negative, then B has higher voltage than A. So for example here, V1 equal to 2 volts. So A has 2 volt more than B. And here A and B, it's minus 5 volts. So we said A has less volt by 5 volt, or B has higher volt by 5 volt. So let me see here if there's any sort of questions here. The question here says, does this mean that the worse the conductor, the higher the voltage required? Conductors all behave the same, which have almost no resistance to the flow. So there is nothing called worst and better conductor. So I'm not really sure about the question here. There is a difference between a flow of electrons and a flow of current. No, they are the same. Flow of electrons is equivalent to the current. So the current is a flow of electrons. So they are exactly the same. So the voltage can be expressed as a vector? No, In DC, the voltage, yes, we'll have the polarity and the current will have a direction, but all we need to do is just change the sign. When we talk about AC later on, then we'll have a vector, means we will have a magnitude and an angle. Here we don't have an angle, just a direction, is it positive or negative. Okay, I think we are. But didn't you mention the current is flow of positive charges? Yes, the current is a flow of positive charges. Yes. This is the conventional current. It's a flow of positive charges. Okay, now this is the last slide. I'd like to uh, show it to you, which is, let's try to relate voltage and current to nature and to some engineering system that we can visualize. The problem of the voltage and the current, you cannot see them. You see their effect, but you cannot see a voltage. When I tell you that the socket has in your house has 110 volt, you have to believe me, of course. Otherwise, if you go and try to test it yourself, you will be electrocuted. So we see the impact of the electricity when you connect a lamp in the socket. Then the lamp shine because it starts to consume currents, and the impact of current you can see. But we cannot really see it, so sometimes it's hard to understand. So these two examples will make it very clear to you what is voltage, what is current, and what is basically the difference between them. So if we look here to this uh, fall of water. Now, the voltage, if you take it as an analogy about in nature, is the force that pushes the current, which is the force that pushes the current in the circuit. It's here, it's the force of gravity. Meaning, if the water, if there is no difference in pressure or there is no gravity here, the water will not flow. Water will stand still. For example, here, this is my water bottle here. If between the two ends, the pressure is exactly the same, there will be no flow of water. The water will not move at all. Same thing in the circuit. If there is no voltage, there will be no flow of electron. So what is the flow of electrons? The flow is basically the stream of water. The stream of water that we have is basically the flow of electrons in the circuit. So we have a source to make the movement, which is the voltage. The voltage is needed to be able to give energy for the electrons to move in the circuit, like the force coming from gravity. On the other hand, the flow of the water itself, due to the pressure, is the flow of the electrons. If we take this as a mechanical system, trying to, we'll talk about this is the battery, this is a resistance. So we don't know much about the resistance yet, but never mind. But we have a voltage and we have a current. So here, for the water to flow here continuously, you need to have a pump, water pump. What is a water pump? The water pump is the one that is responsible to create pressure difference. So you'll have a pressure difference between 2 points, and this will create the water to flow. If there is no pump, or the pump is not working at all, then there will be no flow of water. Same thing here. When there is a voltage here, there will be a continuous flow of electrons going here. Now, or positive charges, if we say, forget about electrons now. So when we say flow of electrons, we mean positive charges. And this is why, if this is a positive polarity of the battery, and we'll talk about that tomorrow, so we assume that the current going from the positive, not from the negative. You might have studied physics that if this is the battery, this is the positive, and this is the negative terminal. So in physics, you might say that the current goes from here, from the bottom, from the negative. But in this course, we assume always the current going from the positive. This is what we meant by positive charges. So let me see here, end up with the last questions you might have. Does using conventional current affect how we do our calculation? Not at all. There is no impact at all. Yes, yes. If we have more resistance, now we will see about the resistance later on. What is a resistance? Then if you have higher resistance, then you have higher voltage to maintain the same current of flow. Now this resistance in this system of mechanical system is the valve. So if I open the valve or close the valve a little bit, then you are controlling the amount of the flow here. So this is changing the resistance. So to make the flow higher or lower, you can control this. So that's the resistance, and we'll talk about the resistance later on. Oh yes, why we use AC instead of DC? Okay, let me end this. And let me insert a slide. Thank you for reminding me this. Okay. So I will give you a simple example to explain why we use AC instead of DC. And this is for the lab, please, any question you need to know, contact Mike. Mike is the one responsible for the lab. I don't manage the lab at all. So if you have complaints, if you have requests, if you have need information, contact Mike or any of the lab TAs. Also, you can contact them as well. If you have any complaint, please, Amal, you can contact Mike for this. Okay, so maybe there is something wrong in the password. Please contact Mike. Now, let's see what is, let's say, AC versus DC. If you go to YouTube, there is a 45-50 minutes clip called War of Current. It's a very famous clip in YouTube, and this is shows you the war that between two great scientists. The one that is came up with AC, whose name was Tesla, and the one who was proposing DC, which is Thomas Edison. And at the end, AC prevailed. And why is that? Let me give you one simple example. Assume that you want to produce amount. Now, there is something called power. We'll talk about it, which is equal to the voltage times the current. Okay, so assume that, let me make things easier for you. Let me assume that I have here I need to have 1000 watt, and I need to have a voltage 100, and the current here will be actually 10 amps. So to have a source here, my source, I have to move it to the load to consume. The load is consuming the 1000 watt to be consumed. So I have to produce this. Okay. Now, if I produce this amount of power, the 1000 watt, it has to go through the wire. Now, the wire will have a resistance. Okay. Now, the resistance that you will have called R, okay, and the power that is consumed in the resistance is equal to I square times R. So if we have 10 amps, and if this is equal to 1 ohm, only 1 ohm, which is very reasonable value, you will have what we call P loss equal to 100 or 10 square times 1, which is equal to 100 watt. So although I produced 1000 here, there is 100 has been lost. So what will arrive here is only 900. This problem becomes worst and worst once you start to increase the power. So if, let's say, I want to send, instead of 1000 watt, I want to send 10,000 watt. If we want to send 10,000 watt, we'll have the voltage as 100, and the current now becomes 100. Okay, now if I want to see the losses that I will have here, the losses becomes P loss 100 square times 1, which is equal to 10,000. So basically all the power I produced, it become a loss. I lost all of it. I have nothing reaches here. So I cannot transfer a huge amount of power. How AC can help? In AC only we can increase the voltage using something called transformers. Not the transformer, the movie, by the way, something different. It changed the voltage. Okay, so I can increase the voltage instead of 100 volt, I can make it 1000 volt, for example, or 10,000 volt. So if assume that in AC now, I increase this to 1000, so 1000 equal to voltage is 1000, so the current becomes 1, and the losses becomes I square times R. I is 1, I square 1 is 1 times R. So you have only 1 watt loss, and 999 of the power will reach. And as I said, as you increase more power, you need to increase more and more and more voltage. And this is only can be done using AC systems. And this is why the AC system prevail. Uh, Maybe what I said doesn't make sense to some of you or most of you because we don't understand power yet. But once we cover power next class, then you can you understand that. No, we cannot use transformers in DC. We use transformers only in AC system. And why is that? Now this has become very advanced, and maybe by the middle of the course, maybe we can a little bit understand why we cannot have transformer in DC. But we'll not talk about transformer in this course. We'll not talk about much of these things, but this is just to understand the basic concept of this. Let me see here if there is some other questions that I can address. What do transformers do again? Transformers change the voltage. Okay, so if I have 100 volt, if I use a transformer, I can step it up to 1000 volt, 10,000 volt. Now, for example, here in Canada, when we transmit the power between the generation to the cities, if you go to Toronto, you see these huge towers outside the city. The voltage there could be around 220,000 volt, 220,000 volts, sometimes 400,000 volt. Now, when you go inside the city, those small towers, it is around 11,000 volt, or sometimes 28,000 volt. This is inside the Waterloo city on those wooden poles. Okay. Now, inside your house, the voltage is 110 volt. Now, you might ask me one question, okay, which is the following. If the voltage inside my house is 110 volt, and in the towers outside my house, it is basically 11,000 volt. So how come there is a transformer that do the transformation? And if you watch carefully, you see them like canisters, the old ones at the poles. Okay, maybe I will bring pictures later on, but if you go outside your house, look to the poles and look for some canisters that are on top of the poles. If you live in new area, maybe after 2000 2002 3, they changed those ones to small, you'll see them like a green box in front of your house or in front or close by one of your neighbors. Those are also transformers. What they do now, these transformers, they step down the voltage, not step up, because now I'm reaching to the load or your house. So I need to step down the voltage so I can use it. If I enter 11,000 volt inside the house, no one can use it because this is a huge amount of voltage. And if you connect anything to it, it will just basically damage. So I need to step down the voltage. So the transformers, actually we use them at both sides of our power system. At the beginning to step up the voltage and then reduce the current to reduce the loss. Once we reach to the house, then we do the opposite. We will need to step down the voltage. The current will increase so that we can use it inside our house. So this is basically uh, so hopefully this is now the password for my course. Yes, it's spring. For anything, any material I post myself, it's spring 2021. All my videos is spring 2021. Any video I will post from now until the end of the term, and the spring S is the capital letter. Um, Today you will just maybe can solve one or two questions from the practice problems, but wait until tomorrow, then you will have a good chunk of the material can be solved. Okay. Okay, guys, thank you very much. Let me stop the recording here. Okay. Okay, and